without further ado, let me introduce Maria Gorinova, who has just finished a PhD here at the University of Edinburgh, and have already started a position in Twitter as a machine learning researcher, Twitter London, and she's our keynote for today. She's done some amazing work at the intersection of PL and ML, static analysis and semantics, and so without further ado, Maria, tell us about program analysis for probabilistic programs.
Thank you, Ahmed, for the introduction, and thank you also to the organizers, Christine and Joe, for inviting me. It really is such a pleasure to speak at LAFI. And as Ohad mentioned, I recently finished my PhD in Edinburgh, where I wrote a thesis about program analysis for probabilistic programs. And this talk is about some of the work that went into this thesis, but more importantly, I hope that this talk will convince you that we really need to think more about what kind of non-standard static analysis, not just static, program analysis in general, we can apply to probabilistic programs and languages for inference in general, and how that can help. So what is the goal of probabilistic programming? To me, the way I understand it, the goal of probabilistic programming is ideally to give a set of tools that allow somebody to focus on modeling and focus on applying their own domain expertise without them having to think about inference. But what would that take? What would it take to have such a PPL? So I see the dream of probabilistic programming as having a probabilistic programming language where we have three things. So firstly, the language is general enough so that we can express any sort of thing we like, any sort of model. But also we want it to be user-friendly. So that's in this talk mostly means automatic inference, although it could mean other things. But yeah, we want to be able to express any model we like, and also get automatic inference without having to think about the complex stuff going on behind the inference. And lastly, we also want this to be fast and reliable. So we want to be able to trust the inference results, and we also want it to be scalable, which sadly many methods are not. So yeah, so in reality, what happens is that unfortunately, we don't have such a probabilistic programming language. We have many, and they are all different, and they all have to make sacrifices in different directions. So, for example, let's say that we have a very general probabilistic programming language that can express any model. Then, because inference is hard, and we don't have an inference algorithm that is completely general purpose and can be applied to any problem that is also efficient. We don't have that. So such languages are forced to use general purpose inference algorithms that are less efficient. At the same time, if we are to choose a more efficient inference algorithm, then we will have to somehow constrain the space of models we have. And some examples that I show here are, for example, bounded recursion, which is very typical. So like we can't have non-parametric models in that language, or just continuous variables are allowed, or a factor graph is needed, and so on. And then there is another option, which some languages go for, which is that we can have a general language, and we can also have a variety of inference algorithms, some of which are very general and some of which are not, and maybe some tools to mix and match them, or construct our own inference algorithm. And Gen, for example, has such an approach. And then, even though we are able to have fast inference whenever the model allows, and the language is also general and we can express anything we want, it is less user-friendly because we have to do extra work. We have to understand, as a user, we need to understand inference, we need to understand the constraints that each inference algorithm has, and so on. And as Fabian mentioned in the talk before the break, these constraints are not always obvious, and it's hard to it's difficult, especially for somebody who is an expert in something else and doesn't want to think about that, to have to deal with it. So basically what I'm trying to say is that even though we really want all these three things, we are sadly in a classic scenario of pick two out of three in the best case scenario. Each probabilistic programming language kind of works around these three axes and finds the right balance for itself where it sacrifices a little bit from at least one of them. So this leads me to the main topic of this talk, which is, can we somehow improve probabilistic programming through program analysis so that we improve on one of these axes? And if you look back here, I, for example, listed stuff such as hint optimizations and hacks needed. So the user needs to kind of like hack through and change their model somehow in order to make something work. And that sounds like the perfect opportunity for static analysis, right? Well, why would the user have to do that? We can maybe do something smart and do it automatically. So that's kind of the line of thinking here. So for those of you who know me, it's probably no surprise that I'll be mostly focusing on Stan in this talk. And it turns out that Stan is actually the perfect language to think about such static optimizations, because it's popular. It has growing community, has lots of developers and just very smart development team who are really good statisticians and who constantly come up with new ways to help their users to express the models they need. So they have all these like tricks and so on that you can use to optimize your models. And just looking through the Stan manual gives so many ideas of how we can try to improve using program analysis on these. So the first, I'll talk about two separate works that are you can read separately. I'll give links at the end. The first one was actually previously presented at LAFI and also at Popol. And it's the one where we introduced Slick Stan, which is a blockless version of Stan. I'm going to explain what that means in a bit. And we also give semantics to Stan, which hadn't been done before. Okay, so basically we started this particular research because we wanted to make Stan more compositional. What you see on this slide is on the right, there is a Stan, and on the left is Slick Stan, which is the version of Stan we implemented. So on the right, we see all these weird blocks over here. And each of these blocks needs to come in order, and it has very specific purpose. And as a Stan user, one needs to understand what the specific purpose of each block is and use them correctly. Otherwise, things are not going to work, or things can be very inefficient. Obviously, that's this sort of block structure, or at least I hope it's obvious that it's not ideal, because it forces us to break good programming practices, for example. So we see that we need to declare variables far away from where we use them. We also, if we had functions, this program doesn't show the usage of functions, but you can have functions in Stan. However, you need to use them in particular blocks, so you can't, it's not very compositional. You can't just have a function that acts a little bit on data and a little bit on model, for example. So we wanted to have something that doesn't have all of this and allows for more compositionality and more flexible user-defined functions. And the two key insights of the work are that, firstly, that the Stan programs are deterministic, and we give that's how we gave the semantics to Stan, which is sort of unusual because we're talking about probabilistic programming language. And then secondly, that we can use information flow analysis to determine which block each statement in our slick stamp program should go to and kind of slice into a stamp program. Okay, so let's just dive deeper on understanding what these blocks mean. So here we have a simplified version of the program before. The data block declares what the data is. In this case, we have some n-dimensional vector y, that is our data. Then we have the parameters. This is what we want to infer. We want to infer the posterior over mu and sigma given y. And then we have the core of the model over here that gives some priors to sigma and mu and defines the likelihood. Also, we have some generated quantities that can give us, it's kind of like post-processing. After we completed inference, we can compute some more quantities. So one way of thinking about this model block is as a way of generating theta, the parameters theta and the data d. However, this is kind of like half true, because what happens in Stan is that each of these statements, these Tweedle statements, are not actually generating sampling around the variable. It doesn't correspond to sampling. It corresponds to deterministically updating some variable. And this variable target is a special variable that is initialized to 0. And every time we have a Tweedle statement in Stan, instead of sampling, we increment the value of target by the log probability, the log probability that the particular sampling statement, so here is gamma 0.1, 0.1 defines. So that what happens is that this means that the entire stamp program is completely deterministic, and it sort of defines the joint likelihood, the log joint probability density of our model. So if we input some particular parameters for d and for theta, what executing the Stan program gives us is the value of the log joint of d comma theta at this particular point theta. And that's how we gave the semantics to Stan, but I'm not going to go into details here because this talk is more about the transformations that followed. So how are we going to take slick Stan, which doesn't have any blocks, and determine how to split this into blocks? Well, it turns out that because each of these blocks need to appear in order, we can identify a particular information flow lattice. So the data and transform data, we say that is of level data in Stan, and then parameters, transform parameters, and model are of level model, and generated quantities are of level gen quant. And we see how the data, the information flows from data through model to gen quant in this program, because everything needs to appear in order. And this is the kind of thing we're going to use in slick Stan. So what we do is that we associate a level type with each variable, and then we can run information flow analysis to make sure that this program type checks. And of course, here we set the types in, so we already wrote in the types, but what the slick Stan user experiences is that they write the program without the types, and we include a type variable for each missing type, infer it based on the information flow type system, and then slice to the Stan blocks. The information flow type system is mostly standard. There are two very small differences to a standard information flow type system. One is this thing here, the curly S of statement S1 and S2, which basically means that variables, once a variable is read at a higher type than itself, it becomes immutable. And this is needed because we need to separate everything in these blocks. And otherwise, if it's a standard information flow system, even if the information flow is preserved, we won't be able to separate the program in blocks this way. And then the second one is that we have this reserved variable target, which is a level model, and it contains the value of the log join function. So that's what SlickStan is. We simply shred the program. We do this optimally so that, because as I mentioned previously, each of these blocks actually, your program can be less or more efficient based on how you ordered your statements into these blocks, because some of the blocks are used in the more intensive part of inference. This slicing helps us to do this automatically, to optimize our program automatically. Another thing that this meant, which we didn't realize at the time, but the next piece of research I will talk about is that actually in this generated quantities block, we can have random variables. We can, or new random variables. We can generate using random number generator. We can sample new random variables. And this is actually equivalent to inference as well of a different set of parameters. But we sort of split inference in two, where in this upper bit of the program, we do inference with one inference algorithm. In the case of Stan, this is HMC. And in the second bit, where it's the generated quantities, we forward sample. Also called ancestral sampling. So with a few little tweaks, we managed to do that in the next piece of research, as well as other things, as I'll show. By the way, if there are any questions so far, that might be a good time to take one or two very quick questions. Okay.
Yeah, there aren't any questions in the chat, so.
Okay.
Yes. Please do put them in the chat.
So the second piece of research, the more recent one, is with Andy Gordon Charleston and Mathis Fakar, and it will appear in the next issue of Toplas. And that one uses this time information flow analysis for detecting conditional independence in Stan probabilistic programs, and also again slicing the program based on these conditional independencies. And we had a particular application of this, which is discrete variable marginalization. So this research started from the following trick, like that you can see when you open the Stan manual. Because Stan uses Hamiltonian Monte Carlo, that means that it needs the gradient of the joint density between the data and the parameters with respect to the parameter, so that thing here. But this means automatically that we can't have discrete parameters, because if we have discrete parameters, this gradient doesn't exist. So the Stan manual suggests a solution to this, because it turns out that you can actually have discrete parameters, you just can't have them explicitly. You need to do some extra work as a user. And that solution that the manual suggests is to automatically marginalize the discrete parameters. And how are we going to do that? Well, firstly, obviously, what happened what we tried to do in this research and ended up being this conditional independence work, is that we try to extend SlickStan with discrete parameters and then find a way to translate this to regular SlickStan or Stan. And so let's see what we mean by this with another example. So in this example, this is what we want to write in this SlickStan plus discrete parameters language. We have a model which it models some sort of the rate the rate of disasters happening. So we suspect that after 2020, from 2020 onwards, the rate of disasters increased. And we want to model this. So we have some observed data Y, which is for T years. Each year, we say that there were that many disasters. And then the rate for the disasters is either E, which is the early rate before, say, 2020, and or is the late rate after 2020. Of course, I mean, I'm saying 2020 just for jokes, because the whole point of this program is that we want to infer when the change point happened. It's a change point model. So what is this year when this change happened? However, this variable that encodes the change is a discrete parameter. So we can't simply write this in stan. But instead, what we can do is we can marginalize it out. So recall that from the previous bit of research I described, we found out that this program, the semantics of this program, is actually the joint between the data and the joint density between the data and the parameters. And in this case, we have, so Y in green is the data, E and L in red are the continuous parameters, and then D is the discrete parameter in blue. What we can do is we can, instead of running inference on this joint, we can run inference on the marginal that doesn't have D, which is just we sum out D. And to write such a program, we literally can substitute. Recall that every such twiddle here is actually doing something to this target variable. So instead of doing this to the target variable, we do it to some reserved variable for each value of D. So we just sort of encapsulate the entire program in a big for loop over the values that D can take. And just as a side note here, this is all multiplication, because I was trying to keep it simple, because it gets a little bit messy otherwise with the whole sum product thing. In reality, this will be in the log domain. So all of this will be plus equals, and all of this will be LPDFs rather than PDF. So everything in the log domain. So yeah, so this is what happens basically. We take the program with the discrete parameter. We encapsulate the entire program in a for loop over the values that D can take over here. And actually here we optimized a little bit because we took these statements out because they don't depend on D at all. And then the interesting thing is that, so that obtains the marginal of P, Y, E, L. But the interesting thing is that we can also resample the values for D if we wanted to have the full posterior, that is P of D, E, Y given E, L given Y, because these values in the ACC are proportional to the conditional distribution P of D given Y, E, and L. So we can just literally use a categorical random number generator to regenerate D. So all of this sounds great. We just put a for loop around the program. Big deal, not very hard. Why do we want to automate this, and why is it hard to automate this? Well, what happens if we have more variables? So let's say we have n discrete variables instead. Then we need to sum out each of them individually. And if we do that naively, that means n nested for loops. Because yeah, we have this function and we don't know how to split it around. So we just have to have n nested for loops. Obviously that's not great. That wouldn't allow us to work with more than, I don't know, a few discrete parameters. Well, ideally we want this to be able to scale to many discrete parameters. So one way, in the worst case scenario, we don't have a solution here, because if all the variables are somehow very densely related, then we can't escape this. We need to sub them out in a nested for loop. However, most probabilistic programs are not like that. Most probabilistic programs are only loosely dependent. Like, for example, a hidden Markov model. So let's suppose we have hidden Markov model. Here is just of length 3. Then what we can do is we can actually nest this in a more efficient way, the sums in a more efficient way, so that we only need n two nested for loops, which is way more efficient, obviously. And the way a general algorithm that can help us with this to determine to eliminate in the right way is called variable elimination. So what variable elimination does is it takes, this is again the program, the HMM from before. So what it does is that it sort of takes into account that if you look at this, the variable Z1 is conditionally independent of Z3 given Z2. And that basically means we can sum out Z1 while only thinking about Z2. We can completely ignore this bit of the model. We can just not think about this. So this is how it works. If we have a factor graph like here, and just as a reminder, for those who might not be familiar, a factor graph is basically a bipartite graph where variables are circular nodes, and the factors are, they describe the joint density between these variables. And they are square nodes, and there is an edge between a variable node and a factor node if this variable node is part of the function, if is in the support of the function that the factor node is. So variable elimination looks at, say, Z1. We want to eliminate Z1. We look at all the factors surrounding Z1, and we merge them together. Delete Z1. We connect them to the previous neighbors of Z1, and we put a sum over Z1 in front of all of this, and that's it. And then we can repeat this for Z2 and Z3 and so on. So the key idea here is that we're going to use information flow analysis and type inference like before. This time we're going to have a different order for the information flow. And we will be able to detect conditional independencies. And based on these conditional independencies, reorganize the entire program so that we essentially, by compiling the program, we compile it into a variable elimination algorithm. And here is the new order that we're going to use for the information flow analysis. This time it's not a lattice, it's a semi-lattice, where there exists a relation between L1 and L2 and between L1 and L3, where L1, L2, and L3 are the three type levels, but there is nothing connecting L2 and L3. And what happens is that, so if we imagine the entire program as a factor graph here, we're going to have some variables of level L1, some variables of level L2, some variables of level L3. And because there's no relation between L2 and L3, that means that there can't be an edge here. So all the program, which is here sliced program in S1, S2, and S3, is going to be one of these three factors. There is no factor between L2 and L3. And going back to variable elimination, that means that if we want to marginalize out these variables that are of level L2, we don't have to think about the variables of L3. We just have to think about this factor over here and the variables of X1. And so that's how we eliminate the variables of level L2. So to relate this to the discrete variable problem, what we do is that we say, okay, I want to eliminate variable d. I say that variable d is of level L2. I say that all the data and the continuous parameters in my probabilistic program are of level L1, because we can kind of treat them as given. And then any other discrete parameters, anything else in our program, is of level L3. Sorry, not of level L3, it's unknown. Then running type inference, we detect what's the most optimal levels between L1, L2, and L3 that the rest of the variables, the unknown ones, will take, and that gives us the conditional independence between variables in the rest of the variables in the program. And this is sort of what, that's probably too small, so I'm going to use, right. So this is sort of what it looks like. If we have here on the left, we have a slick-stamp program with discrete parameters, and that's the HMM from before. And on the right, we have a slick-stamp program where one of them, Z1, is marginalized out. So as you see in this program, it's actually tricky because the statements that depend on Z1 in any way, including through other variables like this, are kind of scattered around. They're not in one place, so we need to find them. And we can find them using information flow analysis. We basically detect where these statements are and which variable needs to go where, and we can put this in the right way without affecting the semantics of the rest of the program. This elim basically means it's a syntactic sugar for the whole eliminate this and put it in a separate variable that you keep track of. Okay, so to sum up, we want to sample both continuous and discrete parameters from a program, but we want to use HMC. However, we can't use HMC if they're discrete parameters, so we factorize the program into 2 bits. One of them is a program where we're going to sample the continuous parameters from the posterior over the continuous parameters. And the other one is a program where, given some sampled continuous parameters and the data, we're going to sample the discrete parameters. And then we run those two separately. And this is equivalent to sampling from the joint posterior. So to take a step back and kind of bring us to the most important piece of information I'm hoping to get across, what we did is, so there are 2 separate sort of factorizations, model factorizations that we did with this. So the first work, the one about slick-stamp, plus a little bit of work that we added with the conditional independence paper, what it does is that if we have a program that defines the joint over some data and parameters, we found a way to find the partitioning of the parameters into θ1 and θ2 such that θ1 is the smallest as possible. And the whole program factorizes like this. And what this gives us is that we can now input only this bit into HMC or other algorithm that it's expensive to run, and then keep this bit, which is very easy to deal with. So this means that we know how to generate θ2 from V and θ1. That's what this means in this particular line. So we just generate θ1 with the expensive algorithm, and then we run ancestral sampling to make to generate samples for θ2. And then the second factorization we did with the rest of the conditional independence paper is that we found a way to find the minimal set θ2, such that if we set if we choose θ1, the program factorizes like this. And this gives us now the opportunity to, if we are doing variable elimination, like I showed earlier, we can just eliminate θ1 in here because this factor doesn't depend on θ1. And I see that I'm quite early, which is great because we can have a lot of questions. I hope people have questions. I just want to say that both of these papers are separately available as papers. And the whole thing is also written in a dissertation, which will be online sometime very soon, but not yet. But yeah. You can email me if somebody really wants to read something, which I doubt, but you know, just in case. Yeah, that's all.
Thanks. And I see people also thanking you. The icons. So I don't see any questions in the chat. If someone wants to ask a question, please raise their hand. In the meanwhile, I have a question. And thanks for the talk as well. So the kind of independence you're taking into account in your second analysis, that's very syntactic. But what if I know some more kind of semantic independence, right? So some specific calculation I do on the variables that generates two independent variables, and I can maybe use that to simplify my factor graph. Can your analysis take advantage of that? Is there any way to extend it to include these bespoke semantic independence results? Do you see what I mean?
Not quite. No, I'm not sure I understand.
So, I mean, a continuous example would be something like the Box-Moller transform, right? And you take two uniform variables and output two normal variables. But if you did the analysis on the computations, right, of course, you're not going to see that they're independent, right? You're doing something quite complicated with the values. And so it's possible that sometimes in my model, I can prove that the outputs of a specific computation are going to be independent, and I want the marginalization to take advantage of that. Is there any way to extend the analysis to take that into account, or is it just completely syntactic and reinvent the wheel otherwise?
I think so, because what you can do is basically, so here when what was I saying? So I was saying how in order to, if we have some variable d that we want to marginalize out, we assign some variables in the program to be of level L1, and then the rest we infer with type inference. But what you can do if you already know that something is conditionally independent of L2, you can put it in L3. So if B is conditionally independent on D given a set of variables, you can put that set in variables here, the conditioning set here, put D at level L2 and whatever the other variables of level L3, and only infer the rest.
Okay, got it. And is that something that you could inject syntactically, or
not at the moment, but like that will be an easy sort of extension to be able to define the type yourself.
That's great. Thanks. And by now, there's some questions in the chat. I see a question by Eric. Can we please put it on the screen? Okay. Can you read it out loud for the benefit of the...
Oh God, off the top of my head, I think so, but I don't quite remember what the differences were of the top of my head. Sorry, that's a very unsatisfactory answer, but maybe we can take this offline, and I will double check and then tell you.
Well, looking at the actual question, you've seen the work. You might want to think a bit about more and take it offline. Yeah, that's good.
Yeah.
Thanks. Eric, do you want to follow up on that? If so, raise your hand. Otherwise, okay. If not, there's another question by Alex. Can you see it?
That's a very good question, Alex. Thank you. I don't know. I think it will. I don't see a reason why it wouldn't be possible to have a decent language with a random number of parameters. And one of the things that makes me the most excited about this work is that it really does seem like there might be a more general framework that we can come up with where we can do all sorts of factorizations. Because here we showed 2, right? But there is no reason why there are not more, and why they shouldn't be relatively straightforward to derive from what's already there. I don't see a reason why it wouldn't be possible with random number of parameters too.
Okay, and I see Eric does want to expand. Sorry.
Hello.
Hi, Eric.
Hi. Yeah. Sorry, I'm just figuring out this AirMeet thing. Yeah, I was just thinking of this paper, a bunch of logic for conditional independence from LAFI'21. Because yeah, I think it would be really cool if we can figure out what the core constructs of conditional independence are, and are these different systems really like expressing them in different ways.
Yeah, I agree. And not just, I feel conditional independence is one of them, but there are other ways to factorize a program, or a joint density. And I would be definitely, if people have ideas about other factorizations that might be useful, I'll be very interested in hearing that. And yeah.
Cool. Thanks. It was a good talk.
Great. Thanks. So I have another question, if that's okay. So one of the appealing and amazing, actually, properties of Stan is that it really has thousands of users, right? Do you have any thoughts, experience on getting this amazing piece of work into to those users, right? They're used to using a very specific kind of Stan, and how they feel about adopting a new tool, learning new things, and so on.
So SlickStan was never meant to be a programming language that reaches the users, if that makes sense. I've never meant for it to be productionized. However, there is definite interest in the Stan community to adopt some of these ideas in next versions of Stan. And they've already started working. So there is a new Stan compiler, because the previous one was in C++, which I get goosebumps from. Like, I would not like to work on a compiler written in C++, but they rewrote the entire thing, and now there is a compiler written on Camel. And actually, they're looking for people to work on this compiler. And the idea is that when this is a little bit more mature, we can implement all sorts of cool things in that compiler, including the original SlickStan work, and also the stuff about the conditional independence and many other things. So there is like a huge opportunity there for people to get involved with this, with the compiler and with other pieces of research. And I'm very hopeful that one day this will reach users.
Thanks. There's lots of love coming from the audience for this. I know Matthias announced that the rewrite, Camel here at LAFI' a few years ago. So it's good to see it kind of a few years down the line. So if there are no more questions and no more hands raised, I think we should wrap it up for today and continue in the lounge. So let's thank Maria again.